understand why it's working or why it's not working. But what I'm going to focus on is I'm going to understand what is it currently doing. And by understanding what it's currently doing, you can figure out, okay, well, what is it not quite doing right and what is it doing right? And that allows you to focus your efforts in terms of debugging. So asking like, what is it currently doing? So I wanted to actually share the example that, that Kenny had sent, and I need to pull up, it's on Moodle and I didn't open up the right window. So I need to log in. So while I do that, I should ask, so the people who just joined, do you want to share anything about the building activity of the LED calculator? So there are a few people who joined just now.
I'm still figuring out. It's a work in progress, applying the growth mindset. I will figure it out soon, but not now.
Okay, did you see my comments about there may be multiple things with your particular circuit?
Yeah, the XOR gates, I have to send you over what's currently on there. I can't quite see what's, like it's not labeled. Well, my glasses are really foggy right now, but I have to see what kind they are. But I thought I was pretty sure that the correct gates. I'll just make sure again.
Okay, so let me share my screen. Share screen. So this was the circuit that Kenny sent. And so as you can see, it's a wiry soup. There's many wires going all over the place. But this is typical for this particular circuit. So in comparison, I will also show some of the solutions that we've had to this circuit in the past. So in, where did it go? Okay, so when we first did this activity, we did not have the blue printed circuit board, and we instead had these manual switches, and we had individual LEDs. So in addition to the part that you built, which had the wires, like this part, there were all these additional wires that were going on with the switches and with the LEDs. And so we simplified a lot of this. We also removed one of the gates because we figured out it was extraneous. And we came up with this much simpler solution. So if you had trimmed wires, your circuit, and you color-coded, your circuit could look as neat as this, but it's not necessary as long as you follow the connections. So what I looked at when I was debugging Kenny's circuit, and this is, the reason I'm sharing this is it's good practice to go through and check in terms of like what you're doing and what you're expecting to do. Not sure why this page is rotated. Let me rotate this page again. 2, 3. So based on his circuit, I labeled and I checked that all the pins that he had connected were all connected correctly. So all of his wiring is correct. He's using gate 4 instead of gate 2. But this is a perfectly fine solution. So the point of this worksheet is that it helps us to debug the circuit and understand which cables are being plugged in on the left end and the right end. So this tells us we need to have a jumper wire from the 6 upper half to 17, column 17 upper half of the board. And this allowed me to debug and check, yes, the circuit he built is functionally correct. So then once I understood that it was functionally correct, the next step was to do different test cases. So you want to test enough cases to understand like in which case is it working and which cases is it failing. So he took pictures of, for different input configurations, what his output was. So like with all the switches on, he was adding 3, because this is A0, it's 2 in the 1's column plus 1 in the, or sorry, 2 in the 2's, 1 in the 2's column plus 1 in the 1's column. So he's adding the number 3 to the number 3, and the answer should be 6. So it should be 1 for S2, 1 for S1, and 0 for S0. And so I wrote out both his output and what the correct output should be. Looking back at the circuit diagram, so this diagram, the easiest thing to check is to check S0. So the output of S0 is just the exclusive OR of these two inputs. So regardless of whether the rest of the circuit is correct, we can check to see if this very simple block is displaying correctly. And what I saw in the Excel spreadsheet is if I just look at the first two inputs and the output, what I observed was that he was getting consistently wrong outputs, and the ones that were getting wrong were always the case when B0 was equal to 0. So when B0 was equal to 1, he was getting correct answers, but when it was equal to 0, those ones were all the ones that were coming incorrect. So from that, I was able to draw a conclusion that somehow his B0 switch is stuck in an on position. Even though he's mechanically switching it to off, it's somehow sticking in the on position. And so answering these sorts of questions or asking these sorts of questions and looking for patterns is a key skill to be able to build and understand circuits. So with that assumption, I did some more analysis as to like the different inputs and the outputs. I studied the rest of the circuit. So looking at this part of the circuit, assuming that this one is always equal to 1. And from that analysis, I actually came up with an interesting configuration that even with the same inputs to the rest of the circuit, he was getting different outputs. And so that led me to a conclusion that somehow there's something that's wrong in his testing where the circuit is having intermittent or transient response that's not consistent. So it's like when he switches it on, sometimes it's on for the switch part, and then it switches off, it may stay on or it may turn off. So from this, the recommendation could be made in terms of what type of testing to do next. So as you're building these circuits, it's very important to have sort of checks and balances. So you build some small part of it and you check that it works. So in the assignment, what we did last time was we first tested the single XOR gate. And I believe everyone who was like, we were working on this together and everyone was able to get the single XOR gate to work correctly. And then we were supposed to build the half adder, which is this part of the circuit, but my instructions were unclear. And so people just started building the whole circuit last time. So what we ideally should do when working with the students or have them go step by step. So they tested this very first XOR gate by itself. That was project 14.1. And then the second thing would be to test the half adder. I believe this was 14.5 before building the full circuit. So piece by piece checking of the project as you're building is a very important takeaway from this activity. The other important takeaway activity, or from the activity, at least from my point of view, is that very first test we did on the blueprinted circuit board, making sure that each one of the lights light up according to the switching back and forth. That's a very simple test that can be done before, and it probably should be done at the end if you can't, like if you have the correct wiring diagram, but something is still not right, check the blueprinted circuit boards. Okay, so those were my main takeaways from the LED calculator activity. Some of the other issues that people face when they're testing the LED calculator and why sometimes they have errors has to do with these pins. So when you're inserting these pins into the breadboard, sometimes not all of the pins will plug in directly. Some of them will get bent underneath and they won't make a contact. Sometimes they get bent outwards. So when you plug it in, be very, very careful and make sure all the pins plug in. These are thinner than the normal wires, and so it's very easy for some of them to not plug in. We did some LED calculator builds a few days ago, and we saw that one of the AND gates that we had plugged in, it wasn't working for AND gate operation number 1, but it worked for AND 4, 3, and 2. And it was because this pin was actually bent and it wasn't making contact with the protoboard. So we built the nice LED calculator circuit. Everything was working except when we had 0 plus 0, it was outputting 2, but everything else it seemed like it was working correctly. And we traced it to a bent pin. So some of the other suggestions for debugging, when you plug things in, make sure they're lined up with the correct column. Double check your wires, the starting row, the ending row. We wrote it in the, or column, starting column, ending column.
We write down the locations in the worksheet so that we know where we're plugging things in. And occasionally you'll have to measure voltages. So to check to see that the inputs are doing what they're supposed to do, you can measure by connecting one of your digital multimeters, so the black leg of the digital multimeter. We wrapped it around a wire and then plugged the wire into the breadboard. So we're measuring everything relative to ground. So some of the things we just checked when we plug into, when we touch the digital multimeter to 5 volts, we get 5 volts. We touch each one of these switches one at a time, and we switch these on and off, and we see, do we get from 0 to 5 volts showing up on the switches? If so, that's the switches are operating correctly. Sometimes we have to measure the voltages at the inputs and the outputs of various gates. Ideally, we would get 5 volts, but in practice, we typically would get actually 4.85 volts here for the 5 volt signal. So when we measure the voltage at the different pin locations, if it's supposed to be on, then we get about 4.8 volts. If it's off, usually it's less than 0.8 volts. So sometimes it might be like 0.02 volts or 0.04 volts, and that's fine as long as it's less than 0.8. The logic gate will think of it as off. If you ever get on your output a number that's in the ambiguous range, the ambiguous range is between 0.8 volts and 2 volts. The logic gate really hasn't decided whether that's supposed to be on or off. And so most likely there's something either wrong with the gate itself or one of the pins is not plugged in. Occasionally we've had some issues with a few of the AND gates, but they generally almost all work. So if you've checked your wires and everything and it looks correct, but you get some intermediate voltage or your circuit doesn't add quite correctly, try replacing the logic gate itself and plug in with a new gate. So I did that with one of the AND gates, and that was able to solve the problem because my wiring was correct, but my circuit wasn't working. So measuring voltages and anything in the ambiguous range, 0.8 to 2 volts, means that something is probably not connected. We saw some cases where people forgot to plug in the power to the gate, or they forgot to plug in the ground to the gate, and that also gives ambiguous results. So just be mindful of those sorts of issues when you're debugging.